Hi friends, very good morning to all. Today I am here for giving a lecture on equivalent focal length of two thin lenses separated by a distance. So this topic comes under the geometrical optics for BSc third sem students. So in earlier class we already discussed about basic things. So it is a very important derivation. So you have to know about basic things, that is what is lens and types of lens. So here we are considering about two lenses, that is combination of lenses. So by using these two lenses we get the final expression. We will learn about one by one. Before, what is equivalent, what is focal length? So equivalent, you already in PVC level you studied about equivalent resistor, equivalent capacitor, or a effective capacitor or a effective resistor. What is that? So that single resistor gives the same effect given by the combination of the individual resistors or resistances. For example, in series RS is equal to R1 plus R2. In parallel, you know 1 divided by RP is equal to 1 divided by R1 plus 1 divided by R2. Like that, here also by combination of the lenses, we getting the final expression or final image, same effect by or same focal length given by the single lens. It means single lens, what is the property or what is the focal length is given, that combination of individual focal length is given, that is sum of the focal length or sum of the lens is equal to single lens. How this will form by studying this topic. So let us start. So equivalent focal length, here L1 and L2 be the two lenses of focal length F1 and F2. We all are know what is focal length, and before only later it is the distance between focal point and pole. That distance is called focal length. For example, if you consider the first lens L1, that focal length is F1. If you consider the second lens, that is focal length F2. Already told what is focal length. So placed coaxially separated by distance d. So distance between the two lenses, that is we represented as a d in here. Let's the ray PA. For example, ray is incident on the first lens, and that is monochromatic, that is single beam. So monochromatic light parallel to the common axis incident on L1 at a height h1. For example, principal axis horizontal, in above there is a incident, that ray incident parallel to this principal axis. So that height is h1 above the axis. This ray after refraction through the first lens is direct towards the f2 dash. After we know about any parallel rays incident on the lens, that should be convex because we are using the convex lens. That's why that's the property is the light, what are the light is fall on that parallelly, that should be converges to the principal axis. That's why that should be meet at f2 dash. We can take any variable. The second focal point, that is second focal point of the lens L1. If delta 1 is the deviation produced in the L1, we have how to you have to know about by seeing this slide. Look at here. For example, it is a PA is the incident ray. It is incident principal axis. It is a principal axis. You all are know what this is a principal axis. It is a convex lens. So we can call it as L1. We can write here also or whatever. So it is a L1. So this is a principal axis. The ray is incident. That is we can call it as name. PA is the parallel ray incident on the first lens. Automatically the convex lens, it should be converges, that rays should be meet at the principal axis. It is a focal point. We get distance between the pole, this is center of this lens, you can pole, distance between the pole and focal point is the focal length. We can call it as a f1. Are you getting? Next we consider another lens. It is a L1 and is the L2. The distance between the two lenses we can call it as a taken distance is small d. So again I will PA, when it is incident, it is meets f2 dash, but before that I will take another lens. So this, after refracting this rays, incident ray for second lens. Are you getting my point? L1, the incident ray is PA, but after it is refracting I place another lens, but this ray is incident ray. Okay, after it again is going to be refracted because of second lens, it refracted and meet at the principal, this is f2. Are you getting my point? So this L2 and f2 is the distance is f2, that is the focal length. F2 is the focal length of the focal point and second pole. This is the first pole, and second f2 dash is the first focal length. It is the second focal length. Are you getting my point? So we all are know about this is the, if rays, if it is not any rays or any lens, it should be moves like that. So that's why I dotted, I taken imaginary line or extended this line to infinity. So after it is that should be in deviation. What is deviation? There is the angle is created between the incident ray and emergent ray. So I will take this refracted, this is a refracted ray, this ray is incident ray. I will take back this emergent ray to backward, that should be meet in the extended ray of the parallel axis. So that's meet here. It is the total deviation, total deviation. So this is the first deviation, that is delta 1. It is the second deviation, that is the there is should be an angle is created between the emergent ray and incident ray. That's why this is the second deviation, is the first deviation. So it is here a outer exterior, it is a interior, both of you here interior angles. It is a exterior angle. Sum of the interior angle equal to exterior angle. I will show in next slide. Wait here. Okay, look at here. So L1 and L2, again I will say it are taken back at meet at this point, this parallel extended line and the emergent ray extended backward extended ray, where it is meet, I have taken one perpendicular line to the principal axis, that should be meet at H2. We can call it as E2 and H2. So what is the angle is created, that is a total deviation. So total deviation is equal to sum of interior deviation, first deviation, second deviation. So this is the effective focal length. It is given by the effective focal length. We can take it here, it is f. Are you getting my point? So how to find out? You will get the final expression, then only you know. Look at it, diagram. So PA, I taken delta 1, here I taken delta 2, exterior delta 2, I taken the name PA, A2 dash, S2 dash, L1. This height, first lens is height is H1. Same height will be in equivalent focal, that is also H1. This is H2. B and L1 is same height is H2, second point or second lens. So these are all point F1 dash or F2 and F2 dash. So I will come back again. You will see here the delta 1 is the deviation produced by the lens. We have delta 1 is equal to H1 divided by F1. So deviation always consider about height into length. Look at the diagram, or we can take a triangle AL1 F2 dash. If you take the triangle, the angle is alpha here, considering here. So let's you in easy way, I will take it is a height and it is a length. So height is H1 from this triangle. Wait 1 second. So here, and that is delta 1 is equal to this corresponding angle, it will be come here. Okay, so it is height divided by length. So height is h1 and length is from this distance to this distance, that is f1. Already we can look back before only this distance f1. Okay, so this is distance is f1 and h1 divided by f1. Next, the emergent ray AB from the first lens is incident on the second lens. So emergent ray AB from the first lens is incident on the second lens. So we already know emergent ray from the first lens, but that should be the incident ray for the second lens. Already I told that one. So this is the incident ray, but AB is the incident ray for this second lens. Okay. Next, and that height is h2 above the axis. After the refraction, the lens L2 meet the principal axis at f2. So that should be rays meet at the f2. We can call it as a emergent ray. The incident ray PA is parallel to the principal. After refraction through the combination, it meets the principal axis at f2. Therefore, f2 must be the second focal point of the combination. You already know first lens is meets the principal axis, the first focal point, and from the second lens it is refracted and meet the principal axis, that is second focal point. So delta 2 is the deviation produced by the second lens. Already I told, again when the incident ray on the second lens, that again is going to be converges, again the making the angle, that angle is that deviation delta 2. Automatically that height is h2 and this focal length is f2. The incident ray PA and emergent ray BF2, we can look at here, that is incident ray AB and refracted BF2, we can call it as a BF2. So when the producers intersect at A2, so automatically we can see that in diagram they are meet at A2. It is obviously that single thin lens placed at A2 and S2. So in that point, if you are placed at the thin lens, it will produce the same deviation delta as the two constituent lens together provide the focal length of these lenses is h2, f2 is equal to f. What we learn from this paragraph, that the combination of lenses produce the deviation is equal to, we kept the lens that the A2 H2 point, we get the same deviation because we can take it as a delta. So delta is equal to combination of deviation, that is delta sum of the delta 1 plus delta 2. So that is equivalent to combination of the two lenses, deviation lenses. Next, look at here. So single thin lens are kept here, single thin lens. So single thin lenses of focal length f is placed at A2 S2 is called as a equivalent lens. Already told what is the property show, that is equivalent. So equivalent or effective, we can call it the effective or equivalent lens. We consider the register is the component, resistance is the property, like that is equivalent lenses if placed that show the equivalent property. The deviation delta produced by the equivalent lens is given by delta is equal to h1 and f1. So here look at here, how we get the, again delta is h1 and f1. Already we discussed delta 1 is h1 and f1. Again you are taking the delta is equal to h1. How it is possible? Look at here. So height, this height, equivalent lens height, and this lens 1 height is same, and this focal length approximately you taken this focal length and this focal length, from this distance to this distance and this distance to this, you compare it approximately, that should be same. That's why you kept this value delta, put the value in delta h1 by f1. In f1 you commonly we take it as a capital F, or we take it here, or there is a small print mistake, you will take it here a capital F otherwise. So h1 divided by f2 F is equal to H1 divided by F1 plus H2 divided by F2. Now your similar triangle AL F2 dash and BL to F2 dash. Look at here. Similar triangle. What are the similar triangle? AL1 F2 dash and BL2 F2 dash. This triangle and this triangle, they are the similar triangle. In similar triangle, by trigonometry, what we learn that sides, for example sides, that is height AL1 divided by that length L F2 dash is equal to, in second triangle, height BL2 and its length is L2 F2 dash. In AL1 we can take it as commonly H1 height and divided by L F2 dash, that is the length of the focal length, that is F1, is equal to BL2, that height is H2, L F2 dash, that we can take it as, look at the diagram, you will understand. It is the AL1 dash, it is the height H1, and L1 and F2 dash, that's total for focal length is F1. Next again BL2, that height is H2, and the L2 to F2 dash, how you can take it as here? By total focal length you differentiate. For example, look at here, what is the difference? F1 total, that is first length to minus difference, this distance, total F1 minus F2, we can get here total distance or focal length. H2 is equal to cross it, cross multiplication, H2 here, this H1 into F1 minus D, and F1 is goes back, or it is remains here, this value is, we can take it here. So again substituting this value of H2 in equation 1, this before equation, this is the equation number 1, put here H2 value. So the equation will be like that. So again H1 F1, H1 divided by F, we here in right side we take it as a H1 is common, so this is right side and left side H1, our LHS RHS H1 get cancelled, so only remaining is 1 divided by F1 plus F1 minus D divided by F1 into F2. Previous here is F1, in last previous we can see here F2, so automatically F1 into F2. Next 1 divided by F is equal to 1 divided by F1 plus we can take it as or separate it, F1 divided by F1 into F2, so F1 get cancelled, that's why 1 divided by F2 minus D divided by F1 into F2. So 1 divided by F, you simplify this equation, cross it, or you take it as LCM, so getting this answer. When you are 1 divided by F, you can take it as an upper part, so that's why it is take it back reverse order, or 1 divided by F, you can take it F, you this below value goes to in numerator, numerator value goes to denominator, so automatically this value. So we can take F1 plus F2 minus D, we can commonly we can take as a delta, so delta is F1 plus F2 minus D. This is called as the optical separation of the optical interval between the two lenses. This is the final expression for the this equivalent focal length. So what we will finally what we understand, by combination of the lenses, what are the individual focal length, that focal length is equal to equivalent focal length. Same in series resistance you were studied about effective resistance or effective resistance value is equal to sum of the individual resistance value, that is combination of resistance equal to equivalent resistance. Same here also, combination of the lenses is equal to equivalent focal length. Combination of the equivalent or combination of the focal length is equal to single effective or a equivalent focal length. So thank you so much. I will finish this class finally. Bye.